Okay, team, let's take a look at our last homework assignment, gradually varied flow. And we're going to be doing some calculations that will lead us to ultimately doing the direct step method of gradually varied flow. So here's the problem set up. I give you a flow rate, 400 CFS, trapezoidal channel, I'll give you a bed slope, I'll give you a side slope, and then a bottom width, and a Manning's roughness coefficient. And I give you all the equations. And if you do want more background from the lecture, I definitely encourage you to read the textbook section 6.6 to 6.8. And it walks you through all the steps that it takes to get to the direct step method. So first we're going to do a critical depth calculation. And I won't spend too much time there, but because we are in a trapezoidal channel, it's a little bit more advanced calculation. We have to use solver to iterate that. So just a quick thing on solver. The idea of solver is that we can use it to iterate values. In this case, we're going to iterate the initial guess of y sub c, such that this equation is equal to 1. And when this equation is equal to 1, this is essentially a form of the Froude number. This is the Froude number squared in terms of discharge. So when that equals 1, we know that we are at the critical depth and we're good. So ultimately, T and A are a function of depth, right? So depth is embedded in these two variables. And so to use solver, we can go to, let's see here. We'll go to data. Actually, it's not under data, it's under analysis. Hang on a sec. All right, so if, it looks like I need to add this on. So this will be a good thing to do together. So let's go to File, Options. And then I'm going to look for add-ins. And then I want to click on the solver add-in. Actually, I think what I have to do is go to Manage Excel add-ins down here at the bottom. Go. And then I'm going to say, let's activate the solver add-in. I'm going to go ahead and activate analysis. That's for statistical analysis, but make sure you check the solver add-in, press OK. And then we'll wait a second. And there it is. So it's under data. And then you can see you got a couple of other add-ins here. So the solver add-in was activated. Click on that. And the way solver works is it says set objective. And so in this case, that's going to be this cell right here. I want that equal to a value of 1 by changing which cell. I want to change y sub c. So it's going to iterate on y sub c until this equation, which is a function of y sub c and all these other variables, is equal to 1. And that's it. And you just do solve, and then it should solve it for you. As long as your initial guess is in the ballpark, right? So if it doesn't converge on a solution, you want to update your initial guess. All right. Then we'll calculate normal depth. That's pretty straightforward. It's just the Manning's equation. We do have to do solver again on this because it's a trapezoidal situation. So you'll want to, Q is a function of all this stuff, right? Y is embedded in there, an area, and the wetted perimeter. So you will want to iterate on the normal depth such that Q is equal to 400, which is the input. So this will tell you what depth you need to achieve a 400 CFS using the Manning's equation. All right, So now we've calculated critical depth and normal depth. We'll compare the two, and then you'll tell me if it's steep or mild. So put your response down here so we can kind of just track that. All right. So once we've done that, we're ready to do the gradually varied flow calculation. And I've asked you, if you come back up here, I say calculate the gradually varied flow profile for a boundary condition of critical depth and 5 feet. So depending on the flow profile, if it's a mild slope, these will go downstream. If it's a steep slope, these will go upstream. So you have to figure that out. Remember, under a mild slope, we have downstream control. All right, now I've calculated these two things, and the way the standard step works, I've got all these equations here for you, is here's the standard step equation. We basically have the specific energy at 0.2, specific energy at 0.1, the bed slope, and then the average slope of the energy grade line, which is average between 0.1 and 0.2. And what this equation says is that we can calculate how far upstream we have to go. So x1 plus delta L, which gives us x2. So this is how far upstream or downstream we have to go in order to get a change in elevation that we specify here. So this is input. So I could say, okay, I'm going to, if my boundary condition is 5 feet, so I'll start with that. And then depending on my flow conditions, so if this is a mild slope, I'm going to be calculating everything upstream from that, right? If it's a steep slope, I'm going to be calculating everything downstream. And if it's a steep slope, then I have to compare this 5-foot depth with the normal and critical depths and figure out if I think it needs to go up or down. So for example, if it's a steep slope and my normal depth is 6 feet, then downstream, I'll start increasing towards normal depth. If it is a mild slope and normal depth is below this, then I want to decrease it. So we'll just do that. So 4.9, 4.8, right? I'm just going to decrement it down. And I'll just take it all the way down. Now, so it's a prismatic channel, right? Trapezoid. So now we just go and do our trapezoidal equation. So for this depth, we come back up, figure out what the area is going to be, figure out what the wider perimeter is going to be, again, based on the trapezoid. We've got that steady flow, so figure out the velocity. And then we can do Manning's equation, right? So just do Manning's equation and solve for the friction slope. So I gave that to you right here. And this is already for US or British gravitational units. So that's our Manning's K value for that for US units. All right. So now that we have the friction slope, we can calculate the next step. So that I left this cell blank right here because we are already saying this is basically x is equal to 0, right? So now we're gonna either go downstream or upstream. In this case, I said it's mild, so we'll go upstream. And so delta x is going to be equals this whole equation right here. All right. And so I actually have to calculate this whole second row right here all the way to SE. And then I'm going to just do everything. So I know Y1, I know Y2, I know V1, I know V2. S naught is given. And then the average is just going to be the average of these two cells right here. So for average SE, I'm just going to do average right there. And so that will give me the average of the two upstream and downstream friction slopes. Okay, so that'll be this particular term right here. So you'll get your delta x. And so it says basically how far upstream or downstream do you have to go until you hit this flow depth? Again, if it's mild, you'll get a negative number, and that's okay. This plot I've set up so that it'll automatically plot all that. And it'll plot the normal depth, the critical depth, all this good stuff. And that will then show you what the water surface profile looks like for the gradually varied flow. So again, if it's mild sloped, we're going to go approach our normal depth, depending on if the normal depth is above or below, right? If it's above, then we'll increase this, but then our delta x will be negative because we're going to be moving upstream away from this. You could give this a big number, say if I gave this 1,000, right? And then it wouldn't be negative, it would just subtract off of that, but we can keep it for 0, it's fine. Now, if it's steep, then our control is on the upstream end, and we're going to be moving downstream, and so the delta x will be positive. So that's just something to keep in mind. And you'll want to remember that I'm pretty sure you'll have to be like incrementally adding them. So we'll see how that goes, but when you do that calculation. But I think each time you just get the next x, and you want to keep tracking, right, the previous x. So if this, say this is negative 200, then I want to say this is equal to this plus, all right, this huge fraction right there, right? So we kind of keep incrementing that. Okay, so you'll end up with a water surface profile. It'll plot all these other things as well. And yeah, it should look like some of the figures that we've seen, right? And you can tell me which kind of flow profile it is. So I've given you some more steps right here, okay? And hopefully that'll help you in your process. But the challenge of this assignment is for you to think about what kind of flow profile it is based on normal depth, critical depth. Do we have a steep slope? Where's my control section, upstream or downstream? And then using this direct step method, do I need to decrease my water surface elevations here or increase? And then I'm going to get negative or positive numbers depending on mild or steep. All right. And we'll have time to troubleshoot this in class too.